Hello. So you might want to tune the volume down because I have a pretty high natural volume. I have no idea. Ah, okay. I'm pretty loud.
I guess I want to.
This is a very easy.
All right, let's get started. Apologies for the slight delay. We're only 10 minutes behind schedule or so. Welcome to Minnesota, those who traveled to our workshop. It's a joint workshop organized by FTPI, our Theory Institute, and our Center for Quantum Materials. The center is supported through the neutron scattering program of the DOE, so you should find a healthy track of speakers and also posters our neutron work. And the Theory Institute is receiving support from the Simons Foundation, which is important to acknowledge, I'm told. So thanks to the Simons Foundation. Also, we have a few changes to the schedule. Botana is unable to travel, and so in her stead, Fiona Burnell will speak tomorrow morning. I think it's the second slot in the morning. And then Ken Plump is also unable to travel, and so his talk was originally scheduled on Thursday morning, and we simply compressed the schedule, which now has 4 rather than 5 talks on Thursday morning, by the last day of the workshop. So without further ado, let's get started. Chris, as the chair of this morning session, and please go ahead.
All right, well, good morning, everyone. We will move on quickly because we're running a little bit late already. But I'm Chris Layton. I'm from the University of Minnesota right here. It's my pleasure to kick off the first session. Andy Mackenzie is our first speaker. He's going to talk about physics of Delafossite.
Thanks, Chris. So you can all hear me, I guess, fairly loud. I want to blow you away with the microphone. So the physics of Delafossite metals is something that we've been really interested in our group for about 1,000 years now. One of the reasons to choose to talk about it here is that there's some very impressive work being done in this department, or this university by Chris's group. There's going to be some posters about it outside, so I'd encourage you to go and look at the developments they've been making there. The work is done, of course, in the end with many, many people. I hope it's comprehensive, but you always have this fear that it isn't, so you flick on quickly, because the main contributors who are also named in this list. Xianglin Kim is completely vital because he grows the crystals. We work only on crystals which we grow in-house. And then I've been really lucky to work with 6 absolutely fantastic graduate students. The 5 here all worked and did their PhDs in Dresden. Graham Baker did his PhD at UBC, but in strong collaboration with us in Dresden. He's now a postdoc in Dresden. A really great guy, so we're very happy. It's been a total pleasure to work with them all. So as I kind of reflected on how much work we've actually done on the materials, I decided that I would give you quite a shallow overview talk, which means that I'm not going to concentrate in any depth or detail on any one of the topics. But I am going to, since this is a film talk, and I'll hand in my slides, no problem. I'm going to make the slides available. So I've cited a lot of references on the slides, at least to our bits of our own work that I won't specifically talk about. So with that in mind, I'll try to give you an introduction to why the thing is interested in me in the first place. Somebody already commented on the name Delafossite. Delafosse was a French crystallographer, and the compounds are named in his honor. So what caught my mind was their extraordinarily high conductivity. Then when you have that high conductivity, what we actually did was to go on and make use of it in many ways, or the high purity of the materials. But I'm going to revert the historical order and address the question of why the conductivity is so high both from our point of view and also mention the work that you'll see in the posters outside from the Twitter group. Then I'll show you a couple of things you can do with photo emission, which you know, is beautifully clean photo emission. Then I'll give you a longer section on the kind of games we've played with mesoscopic physics, both in DC and most recently with Doug Bond and Graham Baker in the AC conductivity. And then I'll invert. So the AC conductivity stuff is the most recent paper we've published from this year. But I want to go back to what I'll call a novel. It's not so novel anymore. We saw a quantum coherence effect, which has not attracted that much attention, and we haven't thought as carefully about it as we should have done over the last few years. I think that's arguably the most interesting thing that's come out of the work at all. So I wanted to end with that and then discuss a few future questions. Okay, that's good. Right, very good. So this Delafossite structure was made famous by work from the Xianglin group at DuPont in the early 70s. They published 3 highly influential papers where they identified the materials that even grew and partially characterized some of the first crystals. What the structure is it consists of triangular coordinated planes of a noble metal in the metallic ones, platinum or palladium. And these are spaced with perovskite layers, but unusual perovskite layers for a cupric or manganite person. The perovskite units are flipped on their side. So it's edge sharing perovskite layers. And that turns out to be important for some of the properties. And in these perovskite layers, for the metals we're interested in, you could put cobalt, chromium, or there's a little bit of work being done on rhodium. Ruthenium, that's a typo, sorry, ruthenium. Rhodium, correct. We have a ruthenite talk yesterday on get on this, so too much. So when you look at the coordination of the noble metal, it's apparently chemically very unusual because it gets coordinated in a linear, simple linear coordination up-down oxygens. And so if that was all there was to the structure, that would be a mirror plane. But the layered stacking means that it's not a perfect mirror symmetry of the material. We're talking about d electrons in the D9 configuration. It'll be 4d for palladium and 5d for platinum. And then with the transition metal sites, I'm only going to talk today about cobalt. So the transition metal site is always in the 3+ configuration. For cobalt, that's in the low spin configuration. So the cobalt just gives you a non-magnetic kind of vegetable space in there. I told you I wasn't going to talk about the chromate or the rhodate. There's a number of papers that if will be there as part of the record of the talk if people want to go and read a little bit more about what our group has been doing on those materials. Let's go back to the, in many ways, simplest ones, the platinum cobaltate and the palladium cobaltate. One of the things which is immediately attractive is the idea that you have a single band crossing the Fermi level. So you have some hope of interpreting what you're going to measure. It's not a completely trivial Fermi surface though, because it's very strongly faceted. So these are very close to hexagonal Fermi surfaces. And that's it, one conduction band, stoichiometric material. So there's one electron per unit cell, just about as simple as you could get. Maybe the closest analogy you could think of is something like a 2-dimensional alkali metal. If you could make a perfectly 2D alkali metal, you would get something like this, except you wouldn't get the hexagonal faceting of the Fermi.
What's the effective mass?
So yeah, very good. So the effective mass is of order. This is amazing, right? This looks for all money like a d electron Fermi surface, right? But what you have is an SD hybridization through the zone. So the shape of the Fermi surface looks D-like, but the parameters associated with it look very S-like. So actually, the mass in platinum cobaltate is about 1.1 electron mass. So you've got very close to the free electron Fermi velocity. And in the cobaltate, it's about 1.5. So again, you're close. Right? So this thing kind of has features of free electron physics and features of singular. So what caught my attention first saw these reported from Tokyo in the mid-90s. It was kind of in the back of my mind that it was interesting. Let's just think about the room temperature resistivity of the metals we know. So there's some highly conducting elements, including the alkali metals. There's some oxides. I don't think this number for strontium malodate is true because we're working on it. We don't reproduce it. But rhenium oxide is certainly true. Iridium oxide is true. Then down here, you have to expand because you have this cluster of the famous highly conducting metals that we know, aluminium, gold, copper, silver. In among those are palladium cobaltate and platinum cobaltate. And the carrier concentration, the volume carrier concentration of these things is about 1/3 of that of a monovalent metal, three-dimensional metal. So the Delafossites actually have the longest relaxation times at room temperature of any known proper metal. Right? You could argue about doped graphene. It's certainly there's questions to be asked there, but with monovalent or close to metallic carrier concentrations, these are the longest relaxation times we know. And they also can be grown with pretty high resistance ratios. So the low temperature resistivity of palladium cobaltate is of order nano centimeters. And you quickly do an estimate that tells you you've got mean free paths of tens of microns in these crystals that you haven't put any effort at all into purifying. Right? You just grow them by fairly, we certainly grow them by fairly, Neanderthal techniques learned from Takatsu and Bino. We don't do any post-processing. And to put the mean free paths into context, if you had a mean free path that long in a gallium arsenide or a 2-deg, you would see the fractional quantum Hall effect easily. So these are incredibly long mean free paths, and they seem to be coming for free. So our approach to investigating why this is was to do an experiment which is really kind of horrible conceptually. You take your beautiful material and you junk it up to see what's going to happen. And the reason that you're doing that is that you always wonder in the modern world, when you have a very high conductivity, do you have a very good material, or do you have some scattering matrix elements that are preventing backscattering and allowing you to work with a crap material and get a great result? Here we're going to see that, and this is something that Chris's group and the posters outside will emphasize, it's a very interesting combination of the two things, at least.
Indeed, but you see enormously high conductivity both at low temperature in defect scattering regime and at high temperature where it's electron phonon dominated.
That's correct. So it has a very weak electron phonon coupling in that sense.
And very weak defect scattering in this sense.
And very weak defect scattering, and we're going to quantify that right now. So what we did is we went to the Sirius 2.5 megavolt electron accelerator in Paris. And that's a very special place because very high energy electrons make almost elastic collisions with solids. So they are unable to dump very much energy in at all. So the chance that these high energy electrons do anything to the material is extremely low. With a very small cross section, some of them will displace atoms. And they create what are called Frankel pairs, which are vacancies or interstitial atoms. The interstitials will often migrate as you warm the sample up, but very often you leave the vacancies in place. And the crucial thing is, A, there's no collision cascades, right? You're not doing a big damage track through the material. It's a point defect you're creating. And B, the penetration depth of these electrons into the Delafossites is millimeters. We're presenting them with the samples a few microns thick. So there's essentially no possibility of multiple defect creation by any given high energy electron. So Veronica, Philippa, and Elena did an incredible job leading these experiments. They also did an amazing job on the analysis because they went back to the original mud cross sections and calculated the scattering cross sections for all of the atomic species. And what they were able to do was to then plot the change in resistivity against the introduced Frankel pair concentration. There's an ambiguity of a factor of 2 here because you wonder where the interstitials are scattering. It's probably just the vacancies that are scattering. But then with no free parameters, there's the 2D unitary scattering prediction. And a lot of the different Delafoscites, once you've got the cross-section sorted out, all sit on that. What that tells you straight away is that there is no scattering cross-section suppression of the electrons. What you actually have are incredibly pure conducting planes in which the electrons are moving. And we have, I'm cutting a long story very short here, but we also could resolve nothing from out of plane defects, although we were creating them in this experiment. And our numbers were that a typical platinum cobaltate sample that we were growing had about 5 defects in 100,000 sites, and a typical palladium cobalt one had about 1 defect in 100,000 sites, was in the planes, was our conclusion. So these are, if you like, just materials whose conducting planes are incredibly pure as grown. And that actually makes them far rarer than things nowadays with backscattering protection. So Chris's group then got interested, and this was wonderful. And they did a number of things, which will be on a poster outside. They grew palladium cobaltate by chemical vapor transport technique and managed to make the crystals bigger and even more pure than the ones that we were growing with the metathetic reactions that we were using. And they did extremely careful chemical analyses, which identified that there are standard levels of defects in the perovskite layers and impurities, but confirmed our result that there are essentially no defects or impurities in the conducting planes. So in some senses, I think you use this word, the perovskite layers are acting like, sinks for the defects, right? So they're probably helping the planes to be so conducting. And because the overall material is so conducting, the screening length is very, very, very short, so that the out-of-plane impurities potentials are screened away so effectively that they have very little influence on the in-plane transport. So I think the two groups basically agree completely on that conclusion. So then the beautiful thing about these, you get this number that it's extremely pure. Then you really want to go and test that. Are you going to see that in real experiments? In photo emission, you really do. I mean, this is some of the, there's a lot of joking goes on between me and my photo emission collaborators. I'm rather irreverent about the technique. This is, as I say internally and would never say in public, this is in danger of giving photo emission a good name. So now I'm going to be getting all sorts of abuse. Very, very clean photo emission spectra. You get this beautiful data. I didn't tell you, but the first family surfaces I showed you were a model imposed on photo emission data. There's almost certainly even matrix element physics in these changes of intensity. This isn't something we've pushed as hard as we could have done. Apparently, yeah.
Are there any oscillation measurements since you have such great?
Yeah, we've got a comprehensive quantum oscillation.
And do they match this pretty well?
Okay, so the materials have slightly, they're not charge neutral surfaces. So if you integrate the photo emission Fermi surfaces, you would say that you were a few % off stoichiometry, but that isn't correct. So the quantum oscillations show you that you're bang on stoichiometry. There's one electron in that Brillouin zone to within the kind of 0.5% accuracy of quantum oscillations. But what, of course, the photo emission does is it tells you have this.
Of course. Okay, thank you.
So these are kind of make you feel glad to be alive sort of data. It's the experimental data. The other really interesting thing, I should say this is the impressive work that's been done by a graduate student ever in my group. Veronica Sunko noticed that the surface states, which also exist because it's not a charge neutral surface, those surface states are strongly Rashba split, but not when the surface is terminated by the heavy metal. It's when the surface is terminated by the transition metal octahedra, and then you've got a problem with your intuition. But within about 50 months of starting her PhD, she made the measurements, came up with the answer, which I'm not going to give you today because I don't have time to talk through it all, but I can do it in private. Made a model, made a prediction, took new data on palladium rhodate, which confirmed her prediction. And you know, if we could all do work of that quality, I'd be extremely happy. So there's some very interesting surface physics. There's also ferromagnetic surface states when you terminate with the palladium or platinum. So there's definitely quite a lot of interest in the surface of these materials these days. And the Rashba deductions made from the photo mission tell you there would be some very special, well, some rather special spin selection rules when you do quasi-particle interference in STM. And Peter Waals' group at St Andrews have indeed seen that those selection rules are obeyed and deduced a very long spin coherence length, which you might expect. Yeah.
Can you say something like stereo-like textures using some nanosquid?
It simply hasn't been done. It simply hasn't been done, so I don't know. Yeah. But this is the top layer. I mean, this is really a certain you get. So you'd have to be quite careful when you're using techniques that are also going to be sampling down and averaging over the bulk. Anyway, I just wanted to say that for interest. I learned a lot from the process of studying these materials. But what we were interested in from the beginning was to use them as test cases in a program of research we wanted to start about using focused ion beams to sculpt samples into designer experimental shapes that would just suit the experiments you were doing. So there's some examples of what we can do. We take the single crystal and we cut it as we want, and we end up with very well-defined geometries. Now, one of the first things that we did when we were doing these kind of experiments was to study how the resistivity or the flow resistance of a bar changed as we changed its width. And what we saw in 2016 was that if we made the measurements, we got data looking like the black dots. And if we analyzed them with what turned out to be a flawed model, we would say that if you were purely ballistic, you would get something like the blue line. If you were allowed yourself a small hydrodynamic correction to that, so you included what's called momentum conserving scattering in your theory, then you would get the red line, which matched the data much better than the blue line. Now, as it turns out, probably the conclusions we drew there were correct. But the thing that we missed was the importance of the hexagonal Fermi surface. So we did the analysis with the models we could write at the time, which had circular Fermi surfaces, and then subsequently discovered that that was not a smart thing to do, right? And the reason it's not a smart thing to do came from some work that Maya Bachmann did during her PhD, where she noticed in several mesoscopic experiments that the transport itself becomes strongly angle dependent when you get down to low temperatures and the mean free path becomes so long that it's much longer than the scale of your device. So here's one, you know, the games you can play are beautiful. So there's one meander track, the current's going all the way through that meander, but we have the legs of the meander at different angles. And the two extreme angles in hexagonal symmetry would be 30 degrees and 0 degrees. And you can see that up at 100 Kelvin, when your scattering length is shorter than any characteristic size scale of the device, you're isotropic, as you should be for a triangular lattice. But then when you get down below that, you get to develop quite a pronounced anisotropy. And this is early work. We can make the anisotropies up to about a factor of 5 now between the easy and the hard direction of transport. So this is a cool effect, but we didn't take it into account when analyzing the 2016 experiment. So I'm just in general, we're the only group in the hydrodynamics game who have realized that actually disentangling ballistic forms of non-local transport from hydrodynamic forms of non-local transport is a hell of a lot more subtle than anybody realized about 10 years ago. So that's ongoing work. The other thing that that Maya did, and that's published in Nature Physics now, that's an out-of-date reference. The other thing that Maya did was something called transverse electron focusing. And that was incredible because there you're looking at electron focusing in a magnetic field and you're probing it with contact a certain distance apart on your device. And she could see beautiful focusing peaks with contact separations of 35 microns. So, you know, if you want to do an experiment that makes you believe you have a tens of microns mean-free path, that's the clearest way you can do it. So that was all very nice work too, I think. Then Philippa McGuinness and Alina Jacquinat started playing with a classic ballistic experiment from the 1990s, where you would make your material into squares, right? And so people were doing this with 2DEGs in the 90s. If you may do it in a material whose Fermi surface is circular in 2D, then the symmetry of the problem is defined by the lower symmetry of your device. But that's not the case when you have a hexagonal Fermi surface. You lose some of the mirrors that you were going to have in that, and you expect that you're going to have you know, hard and easy directions for transport, and all of these things were observed. Again, don't have time to go into it in detail. But what we did is we made the squares, and they made them big, 95 microns, and then they sequentially made them smaller and more smaller to study the ballistic regime being entered and what it would do to you. And one of the things that it did to you was this, and this was a day when they came to the office saying, oh my God, we thought we'd made a decent device, but look at what's happening. So this is the apparent Hall voltage, meaning that you've gone to running current this way and studying the transverse voltage. And the old timers will know from mesoscopic physics that this is a very incorrect inference. It's completely asymmetric. So does that mean that time reversal has been broken in your non-magnetic material? It does not, because if you then go and read the famous work from Büttiker, who extended Landau theory to multi-terminal devices, including current conservation and time reversal, the sort of modified generalized Onsager relation that you have to obey doesn't just involve reversing the field, it's the symmetry, it involves reversing the field and permuting the contacts. So they did that, that's what they measured. So you do the transformation and that's what you get. I mean, it's very super cute. So, and we have an extremely short Fermi vector compared to any semiconductor device. So we were actually able to do a Landau-Büttiker analysis with 12,000 quantum channels going through our contacts and get sensible results in real units for the voltages we were seeing, right? And so, you know, again, this is, I don't know, cute, it taught us a lot of physics, but you might say it's, you know, you could have anticipated all of this if you were smarter. How long do I have, Chris?
5 minutes left,
Right,
just under.
that's about right. So that was fun, and together it absolutely proves that we have these incredibly long mean-free paths that the resistivity told us we had. But now, oh yeah, and then now here's two interesting things. So recently, Graham Baker, we've just published earlier this year, the work that Graham Baker and Doug Bond did, where they went and they used this world unique bolometer that they have at UBC, and they studied the frequency dependence of the microwave conductivity over a decade and a half of frequency. And what they saw was that depending on the angle that they cut their samples and set their currents going around compared to the Fermi surface, not only did they have a numerical anisotropy, which people had expected, they also had an anisotropy where it changed the power laws they were seeing of the frequency dependent conductivity. And that we hadn't anticipated. Graham's a smart guy. This was an experimental PhD. He wrote a full electrodynamic Boltzmann code and was able to understand that this is coming dominantly from ballistic physics, but with a viscous component similar to the size of the one that we deduced in 2016. So that's a detailed paper you can go and read if you're interested. Very elegant experiment that I had nothing to do with conceiving. So now the thing I'd like to close with, and this is, we have theorists in the audience. I think this is really not something we'd anticipated, and certainly not something that we fully understand. So you're doing an experiment where we wanted to measure the C-axis conductivity in FIB devices. So we made a FIB device where the planes were running across the plane of the channel, so that we're passing a current from here to here, and this is a direct measurement of the C-axis voltage drop. Right, it's a very good way compared to standard ways of measuring C-axis conductivity in the layer of material. And then because we had a field, Karsten, Putzke, and Meyer Backlund put the field on, and what they saw were really pronounced. The background's been subtracted here, but you see them with the naked eye. You see very pronounced oscillations in the C-axis conductivity as a function of field resistivity, and the frequencies that you're seeing are width dependent, and they are linear in magnetic field, not linear in reciprocal field. Philip Moll, within a couple of days, said, well, that width dependence, can we understand that frequency by imagining a flux box, if you like, which is one interlayer spacing and the entire width of the sample. And indeed, that just works uncannily well. You can change the width by a lot, and you see the frequency of your oscillations agreeing with that as if it was an oscillation caused by flux of H over E. And if you're going out to that thick one where we still see oscillations, that's about 50,000 lattice spacing. In microscopic terms, that's an extremely wide sample. And yet somehow we're getting a coherent effect. I think nobody could argue that that's not a quantum coherent effect which is causing that. It's not as simple. The flux argument is fine, but if you try and think of summing all of these in standard R&R-Bohm loops, you absolutely get orders of magnitude smaller oscillation size than we could resolve, right? And so we have a kind of hickey theory in the paper because the referees weren't willing to accept it as an empirical paper in the modern world. But we then sent it off for refereeing, and it's cool because this was pretty new. The referee was beautiful. He said, it's just like a Josephson junction, so I don't see what's going on here. Roderick Mercer is senior enough to take a chance. So we wrote back, well, there's nothing at all is new here, except it's not a superconductor, we don't have a junction, and we don't have a Josephson effect. But in some senses, that scales it to me that this was not an expected observation at all. And then Karsten and Maya did something even more didactic for me. A very natural thing. You take the field away from being perpendicular to the plane to rotate it, to be in the plane, to rotate it to being perpendicular to the planes. And you see something which is, I would say, physically so cool. What you see is that your field periodic oscillations that you have when the flux loop is determined by the dimensions of the material, they change to inverse field periodic oscillations when the flux loop is controlled by the magnetic length. So I personally, even though I'd worked under Hasselhoff, I'd never really fully intuitively understood why this reciprocal field periodicity happened. Well, this certainly tells you why. And you can even see it as a function of field at some angles going from one regime to the other if you've got things tuned right with your samples. So, yeah, I understood a lot. It's cute physics, but what we really don't understand is why the signal is the size that it is. And a flux argument is one thing, but a complete theory is something else. These oscillations go up to about 50 Kelvin. That's also a very surprising thing to see. So the paper was published in 2020. We haven't done any more work on it. Kind of thought others would, but people haven't. So a bit of advertisement to the theory community. I believe this is an interesting problem, and it might be cool to see people thinking about it a bit more carefully. My time must be up, so there's my summary. I'll stop now, and I'm happy to answer any questions.
Joe. So Andy, even if there's no pure hydrodynamic regime, right, we still have the, from the feeding that we showed, there's a, momentum conserving, collision rates. Do you have some intuition of where this is coming from?
Yeah, we've been doing a lot of work on that. Graham Baker has really helped my understanding of these issues. I think I'm responsible for introducing momentum conserving to the literature, and that's a terrible term, so I apologize to the world. Because you don't need pure momentum conservation to get these apparently viscous effects. So if you imagine it's been done, I think it was even done in Landau and Lifshitz, to decompose into Fermi surface harmonics, right? The second harmonic is the thing that, with scattering in the second harmonic channel, will give you a viscous-like response.
Right.
And what we believe here, we Graham's even modeled it, is it's because we have all of these out of plane impurities, and they're giving very, very shallow potentials in the plane. So it's an impurity scattering, it's not temperature dependent, right? But it's momentum conserving enough to put a big term into the second harmonic. So you can, and we're not the only people here, so Ellie Zeldorf's group have published these squid measurements of current vorticity that they can control in one of the chalcogenides, right? They don't see any temperature dependence or extremely weak temperature dependence to that effect. So they attribute it to similar ideas of very weak scattering potentials coming from surface scattering because it's a 3D material, right? And so this is part of why I say one of the things we've really understood there is that these apparently hydrodynamic effects are much more subtle than you would think. And probably only in graphene and the low density semiconductors would you be able to call it traditional hydrodynamics in the way that we thought about it.
No, correct. Very nice talk, Andy. So my question is regarding the high conductivity in Delafossite. So do you think the platinum layer that is sandwiched between the cobalt octahedra is cleaner than the pure platinum metal itself?
It's so pure metals, right?
In terms of intrinsic defect.
So metallurgy is a lost art, right? We really can't do metallurgy nowadays on elemental metals the way they could in the 60s. The purity that they took elemental metals to with a lot of care was incredible. I think there's a guy called Royal Stark, great name. He did quantum oscillations, the Stark orbits and things, on a sample of magnesium metal with a resistance ratio that he said was 250,000, right? And so undoubtedly, if you purify the crap out of platinum metal, you can get mean free pass of 20 microns in platinum metal as well. But you have to work extremely hard to do that. You're probably going to have to electrotransport, you're going to have to do a lot of things to sweep the impurities out. What this is getting you is about a defect concentration. These guys infer 1 part per million just from the way the crystal chemistry works between the two layers.
I'm more like thinking of vacancy defect, not the impurity defect. And I'm wondering if
vacancies, you know, because vacancies are what we were putting in, and we could see that the resistivity was going up linearly as a function of vacancy concentration. And you can extrapolate that back and then you can work out very similar numbers. So the vacancy number, whether they're impurities or vacancies, they're sitting in that plane at a concentration of between 1 part in 100,000 and 1 part in a million.
I'm also still concerned about this item 1 and 2, and couple of things. First, you mentioned that the impurity in the whatever bed layer are well screened, but it should be other way around. You have very high Fermi velocity, which means low density of states, and low density of states is actually low screening, bad screening, not good screening. You expect good screening to be in very heavy materials with large density of states.
Okay, as usual, you've said something very thought-provoking. We have a metallic KF. So our thinking, which you can dispute to me afterwards, is that the screening length is going to be something like 1 over KF, which is going to be extremely small.
Okay, that's a question. The other thing is, that you write here explain about defect scattering, but as we discussed earlier in your talk, there's also anomalously weak electron phone coupling. Is there any understanding of that? Are there calculations for electron phone coupling? Why it's not why so weak?
Calculations, saying that the electron phone coupling is very weak.
So it's like order of magnitude weaker than copper or silver?
It's of order, copper or a very weakly electron phone uncoupled metal.
But your room temperature mean-free pass is still much larger than in copper or silver.
Yeah.
So that must be several times
Yeah.
like order of magnitude weaker. So how come?
I don't know.
My final also very short question.
Yeah.
You have optics. Does plasma frequency agree with your concentration effective mass? And does optical
Within 20%, yes.
and the optical relaxation rate is also consistent with everything?
Yeah.
Okay.
And it's a very clean system because it has no intraband stuff. It just
Right,
has the
right,
band
right,
stuff, then nothing, and then a bit of intraband. I can show you the paper.
Okay, I think we have to move on, but thank you very much. All right, so we have one more talk and then a break. We're probably going to shorten the break, I think, to catch up a little bit of time from our late start. The next talk from Riccardo Comin at MIT, he's going to talk about ARPES as a probe of quantum gym. You can just return to
Okay, yeah, actually, my talk is changed. I'll be talking about Mandelbrot's multiferroics, because it seemed like a better fit for this session. Talked by Andy and some of the subsequent talks really much focus on materials properties. So I changed from talk to focus on technique to one that's focused on interesting systems, including one that has, well, I'm going to talk about ferroic states in 2 dimensions. Yeah, so we started working on this in about 2020. I think it was right after COVID. At the time, we knew almost nothing about multiferroics, and we had done very marginal work on van der Waals materials. So I think it's fair to say we didn't really know what we were doing. We started this, but it was a good gamble that we took to kind of explore something that was new for us, and so it's paid off because it's been like there's a lot of interesting physics in these materials, and the work that we started back then is still continuing to speak. So this is the outline of my talk. So I'll do an introduction on a brief introduction on multiferroic orders in 2D, plus spin orders that have chirality. And then I'll talk about this material, which my talk focuses on, which is nickel iodide, and I'll talk about a little bit about basic structure and properties. So there's kind of like an extended introduction here, and then I'll present the main results, which is our ways of probing the multiferroic state of this material in the bulk, and also in the ultra thin limit. This is a van der Waals magnet, so it can be thinned down all the way into a single unit cell limit. And then I'll talk about, at the end of the second part of the presentation, we focus on polarity and chirality switching off, electrical polarization and spin level. So this is work that was done by 3 graduate students in the group. Connor Occhialini, who's in the audience, and he'll be presenting a poster on this material, studying things that I will not discuss here in my talk, more like exciton physics. Chan Song, who I think was the student who conceived originally the whole idea and decided that it was worth trying our luck and explore this these materials. And then Jaruli was joined more recently, and is taking over some of these directions. And then collaborators on the experimental side, I just want to acknowledge the Energetics group from MIT, where they did the nonlinear optical spectroscopy work. And we've got HBN crystals. We use HBN as a substrate to grow some of this nickelite using physical vapor deposition. So those came from Watanabe and Taniguchi. And then very important collaborations on the theory side with the group of Silvia Picozzi and Antia Botana, and very recently with a lot of contributions from Sang-Wook Chong on the understanding of chirality and the properties, the magnetic ground state properties. Of course, our benefactors give us the resources to do this. So just one slide about 2D quantum materials. So I think it's fair to say that this is becoming one of the leading branches of modern condensed matter physics. It's becoming an increasingly more popular playground for quantum matter. What's exciting about 2D materials is that you can realize all the emergent phases of matter that we're very excited about, like including strong correlations. Notably, this is something that's very recent development from the field of crystonics, but also topology and magnetism and various forms of electronic symmetry breaking. And many of these developments happened in the last 6 or 7 years. So this is all fairly recent advances in the field. There's a lot of structural and chemical diversity in 3D materials, which is great. Another great thing about them is that you can stack them on top of each other, so you can create artificial or synthetic quantum materials where you have interfaces between different materials that you cannot create otherwise in bulk or even with thin film synthesis. And this is thanks to the fact that you're not really bound by the rules of lattice matching in these systems. And so in terms of control parameters, there's dimensionality, there's interfacial engineering, strain. Some of these are peculiar to 2D materials and heterostructures, but one of the most important ones is actually carrier doping, which in many of the systems can be realized electrostatically. So you make microelectronic devices, and then you can study electronic phase diagrams using carrier doping, or using gate voltage to change the carrier concentration, which is great. So in terms of 3D ferroic states in van der Waals materials, like the original discovery that you could, the materials induction in single unit cell could sustain long-range ferroic orders is from about 8 years ago, 2016. This is work on thin telluride thin films, which I believe grown, I'm not sure if MBE, but anyway, so thin telluride thin films grown on graphene, and what they observed they're using an STM is that actually there's atomic displacements that generate an in-plane flow. These 2D ferroics tend to, these ferroelectrics tend to support primarily in-plane polarizations. Out-of-plane fields undergo depolarization effects. And what this underscores here, this STM measurement, which is different from the traditional techniques to probe ferroelectricity, is that it's actually extremely hard to probe ferroic states in 2 dimensions. So sometimes people have to resort to this really advanced type of probes. Just a year later, discovered a 2D magnetic order. This was originally found in a 2D antiferromagnet, so in the single unit cell limit of this iron phosphorus sulfide with an antiferromagnet. This was a Raman measurement. But then the big breakthrough came with the discovery of 2D ferromagnetism in chromium iodide and a few other materials in the single layer limit. So using magneto-optical probes as a way to look at magnetism. Looking at magnetism, same as ferroelectricity in the ultra-thin limit, is very challenging because of the very, very small sample volume and number of spins. So traditional techniques such as magnetometry or even squid magnetometry have a really hard time. But magneto-optical probes really emerge as an essential tool to study 2D magnets. So we kind of it was around this time or a few years later that we started thinking about, okay, well, can we realize more, or can we look for more complex types of magnetic ground states in this class of van der Waals magnets? So when we say more complex magnetic ground states, in particular, I mean magnetic ground states that have non-collinear spin structures. So a very popular example is that of spin cycloids. So in spin cycloid, you have that spins rotates in a plane which is perpendicular, so which is parallel to the propagation axis. Through Jolodziński-Murray interaction and the Tsura-Nagaoza-Balatsky model for the spin currents, you actually can realize an electrical polarization from the local inversion symmetry breaking that happens between pairs of non-collinear spins. So pairs of non-collinear spins produce a polarization, and that polarization can be switched if you switch the handedness of the cycloid. And this was beautifully demonstrated. It was compared to the original discovery of type 2 multiferroics. So multiferroics where the ferroelectricity is improper. It's driven by electronic effects such as spin-order coupling, and it's due to the fact that you have a spin structure which breaks inversion symmetry. So it's very much like a spin-induced ferroelectricity. And this discovery was made already more than 20 years ago in the Kuras group, in the material in this terbium manganites. And what you see here is you see the polarization measured as a pyroelectric current that onsets at the nail temperature of this material, and then it can be tuned with a magnetic field. That's direct demonstration of magnetoelectric coupling. That's what got a lot of people excited back in the day about the realization of type 2 multiferroics. It's this very direct coupling between the charge and the spin degrees of freedom, so the possibility of controlling magnetism with electric fields and vice versa, controlling ferroelectricity with magnetic. Now, another interesting type of non-collinear spin texture, which is actually a very close sibling of the cycloid, is the spin helix. So this is also a spin spiral, but now the spin rotation plane is perpendicular to the propagation direction. And that's interesting because the spin helix has chirality. So the spin helix state breaks all mirror symmetry, so it's chiral. The cycloid doesn't break all mirror symmetry, so you can still define a handedness, but it's not strictly speaking chiral. Whereas the helix is chiral, and when you switch the chirality, then you break inversion symmetry. So there's a rigid connection between the inversion symmetry, also breaking of inversion symmetry, and the handedness or the chirality of the helix. And it turns out the Jolodziński-Murray interaction doesn't work for a helix. Because the spin rotation plane is perpendicular to the propagation direction. This would be the bond axis between the two neighboring spins. But it turns out that there is a more generalized spin current model, which goes beyond the Tsura-Nagaoza-Balatsky model, which has magnetoelectric tensors, which under certain conditions can allow for a polarization to arise in spin fluid systems. And so what's exciting about these types of material is that they have spin textures that break inversion symmetry, so they give you a polar ground state. But in the case of the helix, you also have a chiral ground state. So you have chirality, which is very hard to control typically in materials, because chirality doesn't couple to external control fields that we're used to. Chirality doesn't couple directly or bilinearly to electric fields. It doesn't couple to magnetic fields. Chirality can bilinearly couple to the helicity of circularly polarized light. So that's a little bit of a more challenging way to control chirality. And whereas the polar state is very simple, because there you can just switch it with an electric field. And so having a system which is both polar and chiral can introduce this, or can open up new avenues in the study of chirality and in the use of chirality. And in the control of chirality using electric fields. So having a system where the spin texture is both polar and chiral is such that these two properties of the material are very much arising from the very same microscopic degrees of freedom. And so by controlling the polarity, by switching the polarity, we can switch the chirality, the region. So we look for kind of the wide registry of van der Waals magnets. And there's in particular the class of transition metal dihalides, which is very rich, also the trihalides. But the dihalides are 2D magnets, insulators, they're charge transfer insulators that have very simple chemical composition, metal, halogen 2. So you can form them with chlorine, bromine, and iodine. There's a lot of A-site metals that you can put there. There's two different types of structures. But most interestingly is that there's quite a variety and diversity of magnetic ground states. So you have some collinear ground states, typically antiferromagnetic collinear, but you can have some cycloidal states, helical states, etc. So the material that we worked on in the very beginning, and it turned out to be like one of the most exciting ones that we worked since, is nickel iodide, which is a type 2 layered multiferroic. So this is the structure of nickel iodide. So it's a van der Waals material, so it's broken into layers. So these layers are weakly bonded to each other, and you have the nickels that form 2D triangular lattices, the triangular planes, and they're coordinated to the iodines out of it. So if you look at just a single plane, it's a very similar structure to the transition metal type of carbonite, but the nickels form a triangular lattice. And this is the rhombohedral structure. So this is the structure that the material takes up at room temperature. It's very high symmetry. So this white circles are the nickel sites. So nickel is 2+ in this material, so it's spin 1. The material is a magnetic insulator at low temperature, but at high temperature it has this high symmetry. So it has 3 symmetry planes and then 3 two-fold rotation axes, and has, more importantly, inversion symmetry. So we look at the structure in the triangular lattice. So the light yellow, sorry, the brown atoms are nickels. There's 3 dominant exchange interactions in the triangular lattice, at least for the case of nickel. And so there's first nearest neighbor exchange, the second nearest neighbor exchange, and third nearest neighbor exchange. But the first and the third nearest neighbor exchange are really the ones that have the largest super exchange values, constants. And nearest neighbor tends to promote ferromagnetic order, and third nearest neighbor tends to promote antiferromagnetic. So the system does something in between, which is finds the non-collinear ground system. This is very much like sets the stage for the realization of the non-collinear frustrated state. So at low temperature, the material develops highly magnetic order below 59 Kelvin in the ball. So the pitch of the helix is about 7 unit cells in the plane and about 3 unit cells out of the plane. So this is just shown in the plane, but the helix is actually propagating out of the plane as well. And remarkably, what happens when the system goes into the spin helical state is it loses all of its symmetry operations except for one two-fold axis. Okay, so it becomes very, very low symmetry, which is what enables it to be both polar and chiral. So it loses a lot of symmetries, but it retains one fundamental symmetry, which is the two-fold rotation, because that is what allows the polarization, the electrical polarization, which has to be along that. So this has been studied again, the Pura group, originally in the vault, also more than 10 years ago, and there is a multiferroic transition, or there's a magnetic transition. You can see the susceptibility at about 59 Kelvin. There's also a higher temperature transition, but I'm not going to discuss that today. And then you see a dielectric anomaly at the same transition. So this already signals that the charges of freedom are responding to the formation of magnetic spin helical magnetic order. And this can also be further tuned with the magnetic field. So this is direct signature of magnetoelectric. Now, the reason that motivated what the work that we did was the fact that it was proposed that this material in the single layer limit develops some topological spin texture, like skirmins and bicycle, or even anti-bicycle. So it's the spin helical state in the bulk, so it's a single Q helix in the bulk. But in the ultra-thin limit, there was this proposal that the state would become 3 Qs. So you would have 3 helices superimposed on top of each other, and then depending on the relative phase, you could get some topological spin. So we went ahead and made the samples. So these are some thin flakes that are drawn in HDN using physical vapor deposition in our lab. We can, by tuning the growth conditions, we can go from having samples that are mostly single layer to samples that have a distribution of different thicknesses from 1 layer, 2 layer, 3 layer, which is great for the experiment that we do, because in the ultra-thin limit, we use optical probes to study the properties of the magnetic ground state. And so having several samples at the same time of different thickness means that we can study the layer number dependence of the magnetic ground state all in the same time. So then first we wanted to establish how we find we detect this multiferroic, this highly magnetic multiferroic state in the bulk. But we wanted to do that not using traditional techniques for studying multiferroids, such as measuring pyroelectric current for the polar state or doing magnetometry for the magnetic state. We wanted to do this only with optical techniques, because we knew that in the ultra thin limit, that was the only way that we could probe these. So the most basic type of measurement you can do is optical linear dichroism. So the moment you develop a single Q-spin helix, then you break your rotational symmetry. So you expect that the optical response for like polarized perpendicular versus parallel to the helix will be different. So this gives you a reflectivity tensor in this form, produces linear dichroism, and we can see the signature of linear dichroism very clearly correlating with the transitions as seen in the platinum. In the bulk, we see that the linear dichroism jumps at 59 Kelvin. This appears to be a first order phase transition, although that's not settled yet. There is another signature at the higher temperature transition to the first magnetic order, but I'm not going to discuss that in detail. But there's a sudden jump at 59 Kelvin with a rotational anisotropy pattern, which allows us to identify this twofold axis C sharp.
Does it distinguish between helical and cycloidal spiral?
No, this
It
measurement
should,
does.
right?
No, this measurement is. But it tells us that there is a single Q state
Right,
with yes, with a C2 axis, which you can identify from.
We still need to establish that it's helical.
Are there any thermodynamic signatures at this temperature?
What are you thinking?
Well, you say you said that you have a transition from one state to another, so I was wondering if you have any thermodynamic.
Well, magnetometry shows, so there's a first magnetic transition to a state that was originally thought to be a collinear magnetic state, but actually we found recently that it's
Well,
something
for
that's.
example, specific heat.
We didn't measure specific heat, and I'm not sure. I can't remember if this was done in the literature. I don't know if anyone has done it. To be quite.
Okay,
So we certainly did.
okay, thank you.
So we have C3 to C2 rotational symmetry lowering at the helimagnetic transition temperature. Then we look with SHG, so second harmonic generation, which is a probe of breaking of inversion symmetry. And second harmonic generation again shows a sudden jump at 59 Kelvin, so showing very cleanly this transition. If you look at the rotational anisotropy patterns, you can confirm that the low temperature point will be C2, so it really has only one symmetry approach.
Why you don't see domains?
We do see domain.
But then shouldn't you see the 3 copies of the C2 and essentially recover the C3 symmetry?
We do. If you look at different spots on the sample, we do
okay.
see the pattern. Yeah, we do have domain mapping data. You can see.
Okay, yeah. So this is local.
This is a local probe. Yeah. So it probes a lateral area of, let's say, a couple of. The domains are much larger. So we have inversion symmetry breaking at the same transition temperature. And then with Raman, so we did a Raman experiment to look for the signatures in the low energy excitations, because one thing that is missing so far, and this goes back to Igor's question about whether we can tell it's a cycloid or a helix, is that we haven't yet shown that the ground state is chiral. So that's where Raman came to the rescue, because we did these experiments as a function of temperature. At high temperature, there's not a lot that's very interesting. There's a phonon, and then some sort of quasi-elastic scattering, which is probably from some very low frequency spin fluctuations. And then at 60 Kelvin, at the helimagnetic transition temperature, there is an electromagnet that branches off from this quasi-elastic loop. And then the electromagnet hardens and becomes sharper. And so it goes from being overdamped to being like essentially quasi-particle-like excitation at low temperature.
Is this polarization result?
This was in the XY channel. Since cross-polarized, we have data in all polarization channels. We can retrieve all the Raman tensors. So this is the more extended temperature map. You see this electromagnet that's sharp at low temperature, and then it softens towards the transition. It broadens as well. And if you look at the this pair of excitations, it's actually 2 electromagnets. We look at it with circularly polarized light. What you see is that for circular left and right polarized light, the intensity of this doublet peaks switches, which means that there is a pretty significant Raman circular dichroism of order 70% actually. And we see this both in the Stokes and anti-Stokes, so both in the phonon gain and phonon creation and phonon annihilation side. And this is our interpretation is this is a signature of the tire. So the circuit of the Croix Raman tells us that the state we're looking at breaks, or the excitation of the state we're looking at breaks all years. We have done also some Raman tensor analysis on this, and that seems to confirm.
I'm
the
sorry,
argument.
so is this right-left versus left-right, or is it right-right versus left-left?
Incident left versus incident right. We don't filter the outcome.
Oh, then you can't claim that. I mean, you do need to analyze it.
Okay, we can discuss that later,
Okay,
but
yeah.
my understanding is in the study of chiral molecules, the Raman optical activity measurements are performed this way with just control of the incident piece. Anyway, I'm happy to discuss.
Sorry, question. So do I understand correctly, light is incident at 001? And you're looking at
Yes.
the polarization in the plane. What happens if you tilt away from 001? If you come in at an oblique angle or something?
We haven't tried that. It's a bit challenging to move away from, at least in our setup, it's challenging to move away from the backscattering. So, but yeah, that could be an interesting experiment potentially, especially looking at you know, the Stokes versus anti-Stokes.
We can discuss after I have it.
About 5 minutes.
5 minutes, okay, then I got to speed up. So we have a few layer samples. We see that at low temperature, in both bilayer and monolayer, there is a formation of these multiferroic domains. We see this in the cross-polarized imaging. So we see the signatures there already, and we see the different domains. We can track them with the linear dichroism, but most importantly, we can perform the dichroism and the SHG measurements. And we see that going all the way into the ultra thin limits, so now 4-layer, 3-layer, 2-layer, and 1-layer, we have that the transition temperature is reduced, but the multiferroic state is retained all the way to the single unit cell limit, the monolayer limit. So the transition temperature of about 20 Kelvin. So the theoretical model that can actually capture quite accurately the trend in the transition temperature with layer number. I'm going to skip that in the interest of time. There's also some interesting work on accident physics. This is posted by Connor Occhiolini, if you want to go check it out later. And then electrical switching. So the ultra thin limit is very challenging to measure pyroelectric currents. So they go in they're below attoamps levels. So that's because of a very small sample volume. So it's extremely challenging. And one solution is to use a photocurrent type of approach. So we photoexcite carriers. We photostat carriers across the bandgap in this case, and then we look at a photocurrent at 0 bias. So we're not biasing across the contacts, so we let the internal electric field of the sample to drive the photocarriers one way and the other. So we can use this very simple two-terminal geometries, we illuminate with light, and then we can see that if we do field cooling with positive electric field or negative electric field, this is 20 volts or minus 20 volts, we get two opposite photocurrents that onset exactly at the multiferroic, the Helling-Magnetic transition time. This is a very nice probe of the polar states, which is directional too, so it can tell us the direction of the polarization with a specific electrode geometry. And we can do switching, so we can do the whole ferroelectric hysteresis loops. And this is as a function of temperature, so everything goes away at 60 Kelvin, but then you develop this nice and square ferroelectric hysteresis loops. There is maybe a little bit of domain wall motion that causes this sudden jumps in the ferroelectric hysteresis, but otherwise it looks legit. And we can measure this all the way down to bilayer, and in fact also monolayer. So we can measure this all the way down to the very, very ultra thin. So we see these two polarization states, positive and negative, with a little bit of a magnetic field dependence, although that hasn't been explored in detail. And there is interestingly a significant difference in the coercive fields for 20 nanometers thick samples versus true layer thick, which is about 1.2 nanometers. So the coercive field increases by about a factor of 5, going from the bulk samples all the way into the ultra, well, the bulk-like samples going all the way to the ultra thin sample. And we don't yet understand why this is happening. This is still an open question for us. So very last part is about the chirality and switching of chirality. So the Nickel is an example of kinetomagnetism. So the idea here is that when you have a spin spiral, or in this case a spin helix, that has a certain handedness, if you have an electron that moves with momentum in a certain direction, say positive direction, it's plus k, it will feel an effective magnetic field that's coming from the spin tensor. This is very similar in a way to the chirality-induced spin selectivity. Very similar type of effect, but it doesn't come from the chirality in the lattice structure, it comes from the chirality in the spin structure. And an electron with opposite momentum feels an effective magnetic field which is opposite. So if you look at what this means for a band structure, this means that there is a spin splitting in the momentum axis. So there is a sort of like it's similar to a Rajba effect, if you like, but it's due to the spin texture, and it's not due to really to spin orbit coupling. So we can have like a spin splitting in the energy axis, which is controlled by energy scales, which are much larger than spin orbits, such as the exchange. And for a helix that has opposite endedness, we have basically the reversal of the spin splitting. So we have upspin and downspin that are split in momentum, but in the opposite direction. So one way to probe this effect is using the circular photogalvanic effect or measurement. So you want to illuminate the sample from the side, so at an angle, such that you transfer some linear momentum, because you want to probe, like, you want to probe transitions that are on one valley versus the other, and you want to look at the difference in circularly polarized light absorption, and that should, in principle, by symmetry, tell you whether this momentum splitting is taking place. So, circularly polarized light will probe transitions on one side. Circularly polarized left will probe transition on the other side. And then if you deliver linear momentum as well, you're only probing primarily one side. And so you expect the difference between circularly polarized left and right, just from optical absorption selection groups. So this is exactly what we see in the measurement. So the catch here is that you have to polarize the material, but then you have to probe the photocurrent, the photogalvanic effect in the direction which is along the helix, which is perpendicular to the polarization. And we see this very clear switching of the signal. So we have circular right and left, and we see this contrast between right and left. It's also very clear in these types of measurements here, as a function of the angle, the polarization angle. And that goes away at the transition temperature. So we see that there is the chirality basically switches, and when we look with when we do a negative electric field polling, we have one particular chirality, so we have one type of trace. When we pose with a positive electric field, that chirality is switched. So here it's positive, and here it's switched to negative. And so we can keep track of that. So and this confirms that the chirality is really rigidly coupled to the polarization, which now introduces this interesting possibility of controlling the chirality using the electric field. I think I'm way out of my time, so this is the summary of my talk. I'll leave this here, and thanks again for having me. And yeah.
There is a direct way to distinguish helical and cycloidal spiral. If you apply a field in the helical plane, that you should absorb a spin flow, and I would think that it shouldn't be prohibitively large. Did you try to find one?
It actually turns out in this material, it turns out to be pretty large.
And maybe that's where to my second point is that when you are working with your minimal model, may or may not be important, but I don't think that the minimal model should include single site rather than anisotropic exchange, like isotope type exchange. I think in this material, isotope exchange might be probably more important than single site.
Yeah, and that's, sorry, I had to skip that in the interest of time. So the most key parameter in the model is this anisotropic symmetric intralayer.
Oh, I see. That includes, I think, parts.
Yes, yes. So there's a full Heisenberg tensor.
Right. Okay.
With nearest neighbor, secondary, and there's all the different pathways.
Yeah, because of iodine, I would expect it to be more important than single site.
Exactly.
Yeah, so a question about this monolayer limit. So if you apply magnetic field, don't you expect a first order transition into a Skyrmion crystal?
Yes, and this has been observed in several systems that start off with a 1Q state, and then you can stabilize a 3Q state. This particular material, nickel iodide, for reasons that I don't honestly fully comprehend, but the theories do, I believe, is remarkably impervious to magnetic fields. So the spin flux fields, to connect back to Igor's question, is very high. It's in several tens of thousands. So the magnetic field seems to have very little effect, at least in the range that we can probe ourselves in our lab, on the magnetic flux.
Perfect. So, when you do the Raman, I would expect that you're gonna start seeing a bunch of other funnels, or maybe a few other funnels that were not Raman active.
Yeah.
Now that you probe polyimide, so do you see them showing up, or?
Yes. So there's a few nodes that appear, not funnels, but let's see, so, there is a magnet node that appears down. This electromagnet is probably appearing because it's higher active, but it becomes visible now because of the Persian signature.
Oh, so you think these would be, okay.
That would be my guess, yes. Do you see modes that are, like, modes that are folded or remember coming? You see magnet modes appear, but you don't see folded.
Yeah, those are all the new modes that we see. Okay.
Okay, any final questions? Yeah.
Maybe a quick question. So when you measure the photogalvanic response, there's a way of actually extracting the symmetry from the ratio of these response tensors. Are you in fact seeing this twofold? So is one of the components 0? For example, if you measure along the perpendicular direction, you get 0 photocurrent. Yeah, for example, in this experiment, the linear photogalvanic effect would give you also, should respect twofold symmetry as well.
Yeah, so we see that twofold symmetry in these experiments. So the circular we haven't tried yet. These data that I was showing were literally taken 3 weeks ago. So this is very fresh experimental results. So these data were taken very recently. So we're thinking about ways. I'd be very happy.
Yeah, let's.
Okay, if there are no other questions, then we'll wrap up. We're probably gonna shorten the break, right, Martin? So we'll come back at 10:40.
Yeah.
10:40. Thank you.
Then there will be like
It was just like create a new response state. Yeah, set a new response. I think it's just like create. Yes, that would
Yeah, but then it's shining out there. This is not good. You just. Good.
All right. Okay, thank you everyone for coming back. So second part of the morning session, we're going to start with Stuart Calder from Oak Ridge National Lab. We'll talk about long and short magnetic audit and 2D layered random Waals materials. Okay, yeah, thank you very much to the organizers for organizing this and you take present. So, yeah, I'm going to talk about van der Waals materials, motivated by the previous speaker very nicely. To begin, the collaborators in this work. The samples were synthesized at the University of Tennessee in the Manders group. The neutron scattering work was performed at Oak Ridge National Laboratory. So we're lucky to have two neutron facilities, the high flux isotope reactor and the installation neutron source. And the real heavy lifting of the work was done by Riccardo, who is a postdoc at Greven. Okay, so the outline of this talk is going to focus on this 2D layered van der Waals material, MNP SX SD3-X, shown here that where it has these hexagonal layers. At the very end, I'm going to show a couple of slides, if I have time. That'll talk about another van der Waals material, CRPS4, shown here. So the main focus of this talk is the potential neutron scattering results. I'll talk about neutron diffraction. Look at the magnetic structure. I'll talk about inelastic neutron scattering, and then I'll try to motivate kind of combining these two, looking at total scattering and this MPDF technique, where you can start to look at short and long range magnetic order in one measurement. Part of the motivation is really to see if this method actually works. It's quite a new technique. And almost everything, or at least all the data that I collected, is on powders, and everything except one data set in this talk will be on powders. So I'll just try and motivate how you can get a lot of information out of powders as opposed to single crystals. So the very general, broad motivation for looking at these materials is as you constrain the spins, constrain the electrons from 3D down to 2D, 1D, or 0D dimensions, you can start to get a lot of interesting properties. And of course, graphene is the most famous. We have graphite, you can get some tape, peel off a single monolayer, you get graphene, and you get a lot of really interesting properties that led to Nobel Prizes and a lot of research that's happening. This is a very nice review article a few years ago that talks about magnetism in these two-dimensional layered materials. So this is what I'm focusing on in this talk, is going beyond graphene, put in intrinsic properties that graphene doesn't have, such as magnetism and semiconductivity. So there's an ever-growing list. This is, of course, not comprehensive, so I'm going to focus on this material down here, and you can get a lot of interesting magnetic properties in the layers. So the material choice for this talk is the transition metal phosphorus trichalcigenide, so MPX3, where M is your transition metal ion, your magnetic ion, and X is either sulfur or selenium, and then you have phosphorus as well. So these materials show really a lot of interesting properties. You can have energy storage in MPPS3, where you can start to put in the sodium in between the layers and have the sodium batteries. You can start to make real devices, field effect transistors in MMPS3, use magnons in magnonic and spintronic applications for MMPS3 here. So really wide variety of research in these class of materials. Kind of on a fundamental level, you have these magnetic ions on these hexagonal layers. They were discovered back in 1894. This is a reference. I haven't read this reference, but this is when they were discovered a long time ago. So you can get a variety of magnetic ordering. You can get zigzag, stripy, Neal, and so forth. Part of the interest is you have this multiferroic behavior. So you can have a magnetoelectric effect, coupling between magnetism, electric field, ferrotoric behavior, and so forth. Kind of the real interest in this research that I'm going to present is what happens to the magnetism, what happens to the interactions in the materials. So as you start to approach the two-dimensional limit, the interactions in the plane become dominant, and
in these bulk materials, this JC, the interactions between the layers, can to a good approximation often be ignored. And then in this bulk material, you can start to look at quasi two-dimensional behavior. Okay, so this is what I'm going to present, looking at this quasi 2D behavior and start to tune the dimensionality. So the probe of choice is neutron scattering. This really is an excellent tool for magnetic structure investigations. If you can do the measurement, if you have enough sample to do it, have the right technique, it's probably the best technique to get information on the microscopic magnetic information. The neutron interacts differently with the nucleus, with the charge, with the magnetic charge. So you can disentangle the magnetic information and you can extract quantitative information. So you can start to look at long short-range order, exchange interactions, and is upstream dimensionality in the materials. So like I said, everything's on a powder. I'm going to present results on taken on these three different instruments at Oak Ridge. So the HB2A instrument is a powder diffraction instrument at HIFER, the reactor source, where you can see it's quite an open instrument, so it's quite flexible to have a variety of different sample environments. Put in there, you can get to high fields, low temperature, high pressure, and so forth. This instrument Nomad down here that I'll talk about a bit later for this PDF analysis has really a wide detector coverage, so it covers a wide reciprocal space. You have these detectors. So this is kind of sitting where the sample is, and you have these detectors all surrounding you. This is a distillation neutron source. And Sequoia is an inelastic instrument. So you can see there's two people here, Garrett and Sasha, who are some scientists there. These are 1 meter tall tubes. And you have 3 rows as a row here. So you have these really, really big instruments that can start to collect a lot of data. Okay, so yeah, I'm going to look at this series. So I'll start by looking at the 2 end members, MMPS3 and MMPSE3. So for the magnetic structure for MMPS3, this is pretty well known. This is the one data set that I'll show that is from single crystal data, where this group here from France, from the ILL, collected spherical neutron polarimetry. This is probably the most advanced neutron technique you can do if you want to determine the magnetic structure, where you control the polarization state coming in, coming out, and you can really determine the spin directions. This is what they did, where they were able to really uniquely define what the spin angle of this material was, having this angle of 25.4 from the z-axis. So I'll point out here that this is some powder data that we collected on HB2A, the neutron diffraction instrument, where you can see this is in these 2D materials, you start to get these very kind of signatures, peak shapes of the 2-dimensional order that become very hard to fit. This is not a published fit. This is just to really show you the challenges you can get when you start to apply analysis of these data, and this is partly to motivate what I'm going to show, why we chose to do this MPDF technique, where you can start to really analyze the data in a better way. So that was MMPS3 as spins out of the plane. MMPSE3. There were limited measurements. There was one report back in the 80s, I think. Yeah, down here. So we collected a bit more data, tried to determine the magnetic structure. What we found was it was consistent with spins being in the AB plane, so within the layers. If you start to look at substrate symmetry analysis and go down to what should be the maximal subgroups, so the down here R3 bar, these should have spins point along the z-axis. So you actually have to go to quite low symmetry to reconstruct the magnetic structure you see, which is kind of interesting. So maybe there's a bit more to this story as well. So just a bit of an aside is that these 2 magnetic structures are listed in this Bilbao crystallographic server in this MAGEN database. This is really an excellent tool. There's about 2,000 or more than 2,000 different magnetic structures. They show the magnetic space group, and they show a lot of information on what kind of properties you would expect to get from that magnetic space group. So I'd really encourage you, if you don't use this server. It's freely available to go here and to look through. And if you do publish a magnetic structure, to add it to the database as well. Okay, so just a bit of a summary. MMPS3. So these are 2+ spin 5 halves. These have spins out of the layers with a transition temperature around 78 Kelvin. Se3, you have the manganese ions on the same hexagonal layers, and the same 2+, normally spin 5 half. Very similar transition temperature, 74 Kelvin. The spins in the plane. There's some debate on the type of anisotropy and the type of Hamiltonian that should describe these materials, and I'll talk about a little bit later. XY anisotropy being proposed for Se3. You need single ion anisotropy in this material. Maybe you have dipolar interactions as well. And in both of these materials, the single layer can be isolated, and you can see what happens to the transition temperature and the properties there. Okay, so now I'm going to move on to talk about, well, you have this similar layers of manganese ions, different magnetic ordering, different space groups. So what happens if you tune between these materials, and really, can you even tune between these materials? So there has been some recent work where the series of MNP Se3 minus X was synthesized, and you can see that you get a fairly nice series between these S3 and Se3 as you start to tune the ions. There was a phase diagram proposed based on bulk techniques where the transition temperature really doesn't change very much as you tune the non-magnetic ions, but you maybe start to get some interesting magnetic phases at low temperature. And you can tune the band gap as well as you go. So looking at the crystal structure, sulfur version has a low symmetry, C2/M. The selenium version, higher symmetry, R3 bar. Really, these are not linked nicely. There's no group-subgroup relation. All the reports, and really what I'm going to present as well, just kind of assumes that you start with this space group, you move through, and at some point it just nicely changes over to the other space group. There's probably something more interesting going on, and I think this is somewhere where more measurements would be very useful. So yeah, here's the two structures where you can see the layers that are separated by van der Waals bonding.
Are your labels swapped? The second from the right and the second from the left?
Oh, you're right. Yeah. Yeah.
That makes sense.
Well spotted. Yeah. Yeah. This should be S2 SE, and this should be SE2. Yeah. Sorry. I just look at the color. Yeah. So they're very different crystal structures. They have similar layers. Okay, you can see the layer stacking, and the layer stacking is different between the materials. Okay, so partly motivated by the plot or the really bad fit I showed earlier, we started to look at these materials with NPDF. I'll go through a few slides to kind of motivate this technique and hopefully show why it's useful for this material and maybe other materials as well. So here distribution function. This gives the probability of finding it for PDF, for atomic PDF, an atom at a certain distance from another atom. Okay? And this is really an established technique. It's used a lot to look at long range order, short range order, distortions, glasses, very large unit cells, and so forth. So more recently, people have started looking to see if they can do magnetic PDFs instead of looking at the atomic to atomic spin distances, whether they can look at the spin distances. Okay, so magnetic PDF gives you the probability of finding a spin at a certain distance from another spin. Okay, so there's very limited examples, really just a handful, probably half a dozen that have been or less that have been reported. But if you can start to use it, then you can start to analyze long and short range order in a single technique.
So this is showing, I'll just kind of explain what this plot is. So if you consider your central atom with this spin here, if you go out, the nearest neighbor is 3.69 angstroms away. And then if you get this PDF pattern, you would expect to see a peak at 3.69, and this is what you see. And then if you go out to the next nearest neighbor, it's 6.4 angstroms away. Down here, you get another peak, and you go on, and then you can fill out your pattern. And this is kind of firstly, it's a model independent way just to look at what's happening in your structure, and then you can start to fit this. These two differences, the red and the blue, one it's how you normalize your data. So the blue is what you really want. This is if you can isolate the magnetic scattering and account for the form factor and correct everything properly, you get improved resolution. If you don't do that, you get the red, you get worse resolution. So Ben Franson, he was working with Simon Billinge for his PhD, and he developed this technique. And we're using his software down here, so I want to acknowledge a lot of the work that he's been doing. So this is an example that I hope nicely shows how the technique works. So here, if you consider a one-dimensional chain, this is a ferromagnetic chain with spins, atoms separated by 4 angstroms. If you look at your MPDF pattern, you have a positive peak at 4 angstrom, and then another positive peak at 8 angstrom. So ferromagnetic spins gives positive peaks. And if you look at your antiferromagnetic quantity spin chain, the first nearest neighbor spin-spin interaction is antiferromagnetic. This gives you a negative peak in your PDF pattern. The next nearest neighbor is ferromagnetic. This gives you a positive peak, and so forth. And you can see how you can first just visualize your magnetic structure with using this MPDF, and then you can start to fit the data. So just a few more examples. You can see spin density wave, and of course you can look at 3-dimensional ordering as well. So why MPDF for this series? Well, short range order is intrinsic in these 2-dimensional van der Waals materials. So this is a route to start to analyze it. Standard neutron diffraction can be challenging, as I've shown. And if you start to dope in, start to create some disorder, this is also a way to look at that, to see what the disorder is happening at the local level. So the two neutron instruments that we used, Nomad, this is really the standard, the traditional PDF instrument. You get to very large Qmax. The higher the Qmax you get to, the better the resolution you get in real space. The problem with this instrument is it has limited low temperature capabilities. So if you want to look at quantum materials, if you want to look at transitions below 1 Kelvin, you can't do it. You can't apply pressure, you can't apply field, and so forth. So we also use this instrument, HB2A, and this is not a traditional PDF instrument. It has a limited Qmax. But if this is good enough for magnetism, then we can start to use the more complicated sample environments and look at the materials in a different way. So the data is just collected as you would the same way that you would do any diffraction measurement. You put your sample in, you powder sample, you get a diffraction pattern in reciprocal space, you correct for background if you can, and so forth, and then you just perform the Fourier transform and get your PDF signal in real space. So for the data analysis, there's kind of 2 ways to do it, and this dictates what resolution you get. So what I showed earlier for the red and the blue the blue plots. So if you're able to fully isolate your magnetic data, your magnetic signal, you get improved resolution. And ways to do this would be polarized neutrons or doing some temperature difference. In practice, this can get very challenging. The alternative way is you just fit both of the nuclear and the magnetic part. So if you're working in reciprocal space, this is kind of easy or easier. You can typically isolate what is the magnetic scattering, what's the nuclear scattering. If you're looking at your PDF data, everything is kind of merged together, mixed together. So it becomes a little bit harder to do. But you can do it. So the way to do this is pretty simple, really. You just have your PDF pattern. So this is the total PDF pattern from MMPS3, where you have both your atomic, so your nuclear scattering and your magnetic scattering is just mixed into this blue line, then you just fit the red is the fit to the nuclear scattering. And then what you assume is what is left over, the residual, is your magnetic part. So what we say is, okay, this is the MPDF part, and then we can fit this using the MPDF technique. So this is what we did for this material, where we use this R-3 for SE3, C2 over N space group for S3. We fit the nuclear part, the red, what's left over, the gray, we fit this using the MPDF technique. And we're able to get what is a pretty nice fit, I would say, over here for the material. So we're able to use this technique to start to look at what's happening for the magnetic ordering.
So this was all at the same temperature, but shouldn't you have better contrast in some sense if you take advantage of the fact that magnetic order goes away or becomes extremely short range on high temperature?
So this is the temperature difference, or temperature series, sorry. Where we started down at 15 Kelvin, SE3 here, so you can see that the SE3 scattering, this is just the pure magnetic scattering now. Okay, so this is the residual, this is what's left over after we do the atomic fit. The SE3 is weaker, even at 15 Kelvin, and you can see as you go through the transition, maybe there's still some magnetic scattering left, but it dies off pretty quickly. For the S3, you can see the scattering is much stronger, and it persists all the way up to room temperature. Okay, so we can start to extract what we call the ordered moment. So this is just the ordered moment within a real space range. So maybe we go from 1 to 20, I think, in these bits, and this is the moment that's ordered within that local real space range. So for S3, we still have local moments all the way up to room temperature, whereas SE3 dies off. So remember this, so the transition is around 74 and 78 Kelvin. I'm able to extract the correlation length. So S3 is behaving much more like a two-dimensional material. You have correlation up to room temperature. SE3 is behaving very much like a three-dimensional material where the correlation dies off very quickly. This is isotropic correlation. We look at the anisotropic, so looking at the correlation length in the 2D layers and out of the planes. For S3, in the plane, this is where all the correlation is. So just at the transition, you have around 20 angstrom, and then it drops off to around just a bit above 5 angstrom. And out of the plane, you really have very limited correlation, which is really so it's showing that this is a good approximation for two-dimensional material. You try the same thing for SE3 and you just kind of blows up, just get huge error bars. It's really, and the bulk is not behaving like a material yet.
You have more limited temperature range in your correlation length plots versus your order parameter.
Well, this is going below the transition.
Right. So
there's one point missing here. I forget why we didn't collect it there. Will be bad.
But it really truly diverges.
Well, so here this is looking above the transition to look at correlation. I think just go to infinity really. Or it kind of doesn't matter what you choose because of the transition.
If this is normal Wagner physics, then your magnetic moment that you measure at room temperature should logarithmically depend on how large the your spot, whatever, your region is. Do you observe that?
That's a good. We haven't looked carefully to really answer that, but that's a good point. Yeah. Okay, so here, this is looking at the whole series again. So, and this is using the kind of non-traditional PDF instrument where resolution is worse, you can see, but you can still start to fit the data pretty nicely. For SE3, you have this weak magnetic signal that starts to increase as you increase the sulfur content, so the intensity gets bigger and bigger and goes up to the S3 case. And what we find fitting this is that we have this kind of very nice gradual tuning of the magnetic moments as you go across the series. So you don't have just an abrupt change somewhere. You're able to kind of finely tune the magnetism. This theta degree is, so 90 degrees is in the plane, and it starts to move out of the plane. Fairly, you can almost put a straight line to this, and then it's just showing the manganese distance changing. In the next, I guess I've got 5 minutes, so.
Yeah.
So in the next 5 minutes, I'll talk about the exchange interactions, to try and kind of round out the story, hopefully. So, yeah, we performed some inelastic neutron scattering measurements on both materials, S3, Se3. This is the temperature series where you can see we have well-defined correlations, low temperature, just below the transition, you can still see spin waves, but and even at 200 Kelvin, you kind of see some kind of correlated features, although of course it's very broad back. So to look at these, we look at just a simple Heisenberg model on a hexagonal layer. We have J1, J2, J3 interactions. Often you can neglect this JC, and I'll show when that becomes important. Okay, so for S3, this was measured a long time ago, back in the 1998, on a single crystal sample. Shown here, these are the exchange interactions they extracted. We were looking at the whole series with powders, so we started with what was known. Firstly, to say they could reproduce the results. So we collected these data on the Sequoia instrument. This should be okay, yeah, for S3. So here's the data. We plug in these numbers into the model, and it's just a spin wave model, and you can see very nice agreement shown here. Okay, so the powder data should be useful. We can use. So now we moved on to the Se3 sample that hadn't been looked at before. Start to look at the interactions. So firstly, I guess I should point out the main feature of this S3 is that you have this spin gap down here. They were able to use, and they modeled this with just a single ion anisotropy in the material. Okay, and they have a very small JC interaction, which when you're doing powders, essentially you can ignore. A very good approximation. So if you take the Se3 data, if you look at this, you're like, maybe okay, there's a huge gap here. So maybe there's more anisotropy in the material. But if you look a little bit more carefully and you kind of dig down at the low energy part, you can see that there's some dispersion coming out of E equals 0, shown here. And then you're able to model this, the powder data. And you start with theory that predicts the in-plane J1, J2 interactions. You can tune these slightly, and adding anisotropy doesn't do anything. You can't start to model the data. You have to start to put in this. You have to put in a JC interaction, which is an order of magnitude larger than the JC interaction for the sulfur version. It starts to become comparable actually to some of the in-plane interactions. So again, this is really showing that the Se3 is behaving like a bulk three-dimensional material, even though you can kind of exfoliate it down to a single layer. Whereas S3 is much closer to the two-dimensional limits. So looking at all of the whole series, we're able to model the data. So the data is shown here. The model is down here for the whole dispersion, and just looking at the low energy part. You can see you have this very kind of nice gradual change of the excitations. The top of the band drops down. The low energy part, you have this very small gap, and then where you need to put in a little bit of anisotropy, which decreases. And then as you go to this 1.5 case, you start to see the interlayer interactions developing, and you can model these kind of nicely as they start to increase through the series. Well, these are kind of more thoughts rather than answers. So what's happening in this series? Well, firstly, you can have a series and you can start to tune the behavior in a kind of controllable and a nice way. S3 is close to the closure limits. Se3, you have to include the interlayer interactions. The anisotropy. So it's a bit unclear actually why you get this behavior. You're changing sulfur, selenium, so you're increasing the ionic radius. Maybe you're changing the distortions a little bit of the octahedra, increasing the charge, increasing the spin over coupling a little bit. But you're doing all this. You're changing the magnetic.
That again can be an isotropic exchange. I mean, anisotropic exchange would be very sensitive to whether it's sulfur or selenium, because selenium has larger spin orbit.
Yeah. So you're changing all of these, you're changing the structure, you're changing the interaction strength, but the ordering temperature kind of remains the same. So that's a little bit of an unknown thing why that still happens. Okay, so that was the end of that part. I think Chris is standing up, so I will skip through this and I'll show just one plot here. This is the last slide, I promise. Where we looked at the MPDF. This is just a motivated line where you get a lot of information from MPDF and CRPS4, different Van der Waals material, where we were able to look at the spin ordering through the transition, and we could see that in the paramagnetic phase we get a different spin direction than we get to go into the ordered phase. And this is something that really only or MPDF is very well suited to doing. So you can get information correlation length, moments, and also look at different ordering in the paramagnetic, what's so-called paramagnetic short ordered phase, and the long-range ordered state. So with that, I'll show conclusions. There's some papers on the work in being published. Another paper that hopefully will be published soon. We just got released that today. It's on the article. So thank you very much for your attention.
Do you think it may be possible to make a Janus structure with sulfur predominant on one side of manganese and selenium on the other? Because theory predicts that it would be an altermagnetic.
Okay. I don't. Yeah, I hope so, but that could be hard to do. But yeah, I don't know how you control that in the normal synthesis way. But you'd probably have to do thin films to deposit them. Yeah, but that's interesting.
Can I ask a very basic question? So when you changed X in this series, you did it in integer and half integer parts.
Yeah.
So are they all ordered compounds? And what happens in between the integer?
That's a good question. We don't know. So these are very nominal values. Yeah, we kind of showed these just because it's the easiest thing to do, and then you can look.
The sulfur and selenium are ordered in real space in all of these positions.
So the actual ordering of we're kind of assuming they're going in randomly. Right? We don't see any indication that they're starting to order. But we haven't looked carefully enough to really say that.
But in PDF, you would see that structure.
Well, yeah, we kind of did the measurements to show it the wrong way around. We looked at the dope samples with, say, the instrument that gives you bad real space resolution. So when SNS starts up, we can kind of have another look with better resolution, and then we can see if there is order or if it's just kind of random. Yeah,
Because if there's no order, this is so far from Picard's law, it makes you far.
Yeah.
If it's not ordered.
Yeah.
But go ahead.
I've got some questions more on the technical side. So in your measurement of this PDF analysis, have you looked into the a grain size dependence of the result? Like how much would the short range correlation be affected by the boundary of the grain?
No, I mean we haven't looked. Yeah, we haven't looked at that. That's interesting. But yeah, we haven't done that.
And maybe a second. Sure. So is it conceptually possible to do this PDF kind of analysis for given energy slice?
Dynamic PDF.
Yes.
Yeah. You can do it. I've not done it, but there's people doing it, and Kashiyagami, who's the expert in PDF, he's doing that. Yeah, where you look at the inelastic slices. Yeah.
And in your case, you are basically adding up all the energy slices, hoping that it goes to the instantaneous limit.
Yeah. So you just you average over.
I see. Thank you.
Any other questions for Stuart?
Yeah, I have just again about the technique, maybe a short question where I may have misunderstood something. So when you Fourier transform from momentum space to real space, the MPDF pattern that you get, there's surely a random component to the Fourier components of a phase, right? That could have in principle some random offset. Do you need to correct for that at all? Do you need to somehow fix the phase of these Fourier pattern?
No, random offset of what?
I mean, the phase is generally unfixed, right? You should have some global phase to the whole thing. And that affects, I guess, the sign of what you get on the real space side, right?
Yeah, yeah, we don't do that, right? Maybe I can talk to.
Okay.
Sure, do you have any indication of the second magnetic phases that we're seeing from both measurements?
Yeah,
They look like
yeah, I know, I showed that plot, but no, we don't see any mixed, because they said there's mixed phases and some kind of, yeah, we don't really see that, unfortunately, yeah. I just point out that we are running a workshop in July, we can structure workshop, she'll advertise just the beginning students.
Good. Okay, thank you, Stuart. Okay, so we'll move on to the final topic of the morning. It's thermal wall effect in insulating fiber walls and I got it by Xianglin from Washington State.
Yeah, of course. Okay. So I work when
Who is it?
Okay, so first of all, I'd like to thank the organizers for the invitation and giving me the opportunity to this workshop. And so, yeah, our group has also been working on neutron scattering to study the physical properties of materials. Okay, so let me focus on some of our recent thermal transport studies on insulating monovac magnet. And I hope at the end I will convince you that the thermal transport is a very good and important complementary tool to neutron scattering. Okay, so our second and third speaker already gave a very nice and motivation introduction to the monovac magnet. So since I'm the last speaker before the lunch break, so yeah, I'm going to just quickly recap. Okay, so again, from the, in this table here, I just show you some of the monovac magnets, including the tractile headlights and so on. And from this table, we can see that the magnetic property of monovac magnets is very rich, right? The magnetic property could be the ground state could be ferromagnetic, antiferromagnetic, or it could be multiferroic, and some of the materials could even be candidates of condensing liquid. And furthermore, it turns out that the physical property of this system is very sensitive to the external perturbation, like our second speaker mentioned, right? It's sensitive to the strain, it's sensitive to the electrostatic charge, pressure, and proximity effect. Okay, and last but not least, we all know that since this is a magnet, therefore they have some kind of actual applications in spintronics, right? So today I would like to focus on another aspect of monovac magnets, and that's their topological magnetic stations. So we know that in the past 2 decades, right, there have been a lot of studies on the topological materials. They follow the discovery of the topological insulators. For the topological insulators, we know that they are conductive, they are insulated in bulk, but they are conducting on the surface or on the edge. And such an exhaustive electronic properties are protected by the band topology. So following the discovery of the topological insulators, there have been tremendous efforts in searching for new topological states of quantum matter, such as the direct semi-metal, wave semi-metal, and so on. So it turns out that the concept of band topology can be nicely applied to describe magnetic excitations. So for instance, let's say that we have a ferromagnetic Comin system with the spins pointing up, and then because of the Comin geometry, they got 2 dispersive bands across each other, and that's a flat band. And since this system again has the Comin lattice, therefore the inversion symmetry is broken relative to the center of the nearest net bound. Therefore, the electrostatic interaction, also for PM interaction, is allowed. So in this case, these 2 dispersive bands will open a gap at a K point. Okay, and by calculating the Bailey curvature of this gap magnetic bands and then calculate their chain number and so on, it has been shown that these gap magnetic bands are topological in nature. And topological magnetic excitation has been observed in several compounds. Here I just list one of them, which is top 13 PDC. The left figure is the inelastic neutron scaling data, and the right figure is the similarity results. Based on this Hamiltonian, the second term here is the DM interaction. And overall, we can see that they agree nicely with each other. Particularly, if we take a close look, you can see that there's a gap occurs along the K point. And through such a comparison, it was argued that this system, the manifestation of this system is topological. And if we have a system shows the topological manifestations, in the presence of the longitudinal thermal gradient, then what do you expect to see thermal Hall effect? And from this equation, immediately we can see that the thermal Hall signal is directly related to the value curvature of the gap magnon band. So just recap about Hall effect. So we all know that for the electric Hall effect, right, we apply a longitudinal current going through the sample, and then in the presence of the perpendicular magnetic field along the transfer direction, we measure the electric voltage, then we get the electric Hall effect. Similarly, for the thermal Hall effect, we apply longitudinal thermal gradient along the sample. Then we measure the transverse thermal gradient across the sample. Okay, and we could apply such a technique to study metallic compounds. So for the metallic compound, the heat carrier will be dominated by the charge carriers, electrons or holes. In the meantime, this is the beauty of the thermal Hall effect. We could use thermal Hall effect as a form to study the insulating materials. And for insulating materials, the heat carrier will be dominated by the charge neutral particles, such as the magnons and bonons. Okay, so again, thermal Hall effect has been applied to study the metallic compounds. And recently we have applied such a technique to study terbium magnet 166 compound, which is a carbon magnet. And we made various transverse transport, including the thermal Hall effect, density effect, and the electric Hall effect. And for this particular compound, we observed very large transverse signal for all these three transverse transport. And this is tells us that the system actually is topological in nature. And again, today I would like to skip the details of all these measurements because I would like to focus on the insulating compounds. So thermal Hall effect again has also been applied to study insulating compound. And here I just list some of the recent examples, and you can see that some materials could be the garnet, could be the cuprate, or could be even just a ferroelectric strontium titanate. Okay, and it was argued that for this system, phonon is the dominating heat carriers. Even though to the underlying mechanism of some of the systems remains still debating. And magnon thermal Hall effect has also been observed in several systems, only a few systems. Okay, here I listed a couple of examples. One example is the lutetium vanadium 227 system. This is the parallel compound. And then another example is the copper 13 BDC, which has the 42D carbon system that is described in the previous slide. And if we take a close look at the y-axis scale of the thermal Hall conductivity, we can see that the thermal signal of both compounds is very small. Right? It's in the range of 10 to the minus 3 or 10 to the minus 4 watt per meter Kelvin. Okay. So about 6 years ago, there was an inelastic neutron scaling study on chromium triiodide, where chromium occupied on the honeycomb lattice. And since it has a honeycomb lattice, the divergent symmetry is broken relative to the secondary snaggle bond. Therefore, the DM interaction is allowed. And from the inelastic neutron scaling study, we can see that there's a magnon gap opening at a K point as well, which is very similar to the copper 13 BDC that I showed you earlier. And the figure on the left is the similarity results based on this Hamiltonian. And again, the second tab here is the DM interaction. Okay, and we can see that again, the experimental data and the similarity results agree very nicely with each other. Therefore, they argue that this system shows topological manifestation. So this actually motivates our thermal transport study that I'm going to show you in today's talk. So the first compound that I'm going to show you is the vanadium triiodide, which has the similar crystal structure to the chromium triiodide. Here the magnetic ions, vanadium ions occupied again the honeycomb lattice. And from the bulk heat capacity and magnetic split magnets, we know that the system has a structure phase transition occurring at about 76 Kelvin, followed by a ferromagnetic phase transition at about 50 Kelvin. Okay, and from the magnetic splitting measurements, it was argued that the EG axis was along the C direction. And recent single crystal neutron diffraction measurements done by Oakridge Group and a group in Fudan University found that actually the EG axis of this is of vanadium triiodide is slightly tilted away from the C direction. And both the neutron diffraction as well as the synchrotron X-ray diffraction found that below the stratal phase transition, the honeycomb lattice of the vanadium ions is slightly distorted. So this is like this, these two photos, this shows the sample that we grow, single crystal samples that we grow using the chemical vapor transport. And we carry out this bulk magnetic splitting maintenance. And again, we found that the system orders about 50 Kelvin and has a large spin moment along the C direction. So everything is consistent with the literature report. So now let's take a look at the transport data. So we use the so-called one heater and 3 sensor technique to measure both longitudinal and transverse thermal conductivity of this system. Now let's take a look at the longitudinal thermal conductivity first. So this figure shows the longitudinal thermal conductivity, so-called kappa XX, as a function of temperature. Then we measure at 0 field and 7 Tesla. And immediately we can see that the system shows two anomalies. Right? One occurs at about structural phase transition, the other occurs at TM.
So this is highly reproducible as we turn.
Yeah, this is highly reproducible. I'm going to show you in the next, in one of the next slides.
Could you comment a little bit on the setup? So you're measuring voltage between these two, you're measuring what exactly? So you have a thermal gradient along X, but you're measuring the voltage.
Yeah, so this is the schematic of the setup. We imagine that we put a heater here.
Yeah.
Okay, we heat up this end, and here is the heat sink. We kept the sample to the heat sink directly. And then we put 3 sensors, T1, T2, T3, set of sensors, and then we measure the temperature directly.
There's no current flow anywhere. And it's all
this is insulating.
Right,
compound.
but also everything is floating, so there's nothing.
Yes, everything is floating and everything is turned on, of course. Yeah. Okay, so as I just mentioned, here we observe 2 anomalies associated with stratal phase transition and magnetic phase transition. And furthermore, we found out that in the presence of the 7 Tesla, the thermal conductivity increases. So as we just point out, this system is an insulating compound. Therefore, they got 2 dominating heat carriers. One is macron and the other is phonon, right? And these 2 quasi-particles could scatter each other. So A0 may scatter each other, and A0 field, the phonons are scattered by the macrons, which is going to lead to the separation of the thermal conductivity. Then when we apply 7 Tesla magnetic field, we are going to push out the macron band, and as a result, the macron population is going to reduce. And this is going to lead to the reduction of the phonon scattered by the macrons. And this is going to give us, or this is going to at least partially restore the phonon contribution to the total thermal conductivity. And this is, again, this is exactly what we observed, right? In the presence of the magnetic field, the thermal conductivity is enhanced.
So just to come back to my question, so this is reproduced also from sample to sample.
Again, I'm going to show you. Yeah. I'm going to show you in a couple slides. Okay, so this slide shows the thermal transfer measurements, thermal Hall measurements, transfers, thermal transfer measurements, and particularly this is focused on the figure on the right. You can see very large thermal Hall signal over a wide range of the temperature. Right, they got 2 main features. One is again the magnitude of the thermal Hall signal. In this case, is about 10 to the minus 2 watt Kelvin per meter, which is almost 1 to 2 orders larger than the data I showed you earlier, right, in the introduction. And second is that we can see A0 magnetic field, the thermal Hall signal is still very large. It's almost the same as the saturated value at 0.5 Tesla in this case. So this tells us that in our system, we have anonymous thermal Hall effect. Okay, and again, here we measure the thermal Hall signal over a wide range of temperature from 4.7 Kelvin all the way to a temperature close to the transition temperature. Okay, and then from here, we could extract the temperature dependence of the anonymous component of thermal Hall signal. And this is what we got. Now come to Martin's question. So we try to reproduce the measurements of many samples. And here, this is so some of them, and you can see that this is the thermoconductivity, and this is the temperature dependence of the thermal signal. You can see that the other features are very similar, right? Except the magnetic is slightly different. For instance, you can see that for this sample one, the magnitude of the thermal signal is much smaller than this. And the reason is because this sample one is really the first sample that we measured. So at the time, we did not notice that the sample was so sensitive to the moisture. So the device was made in air, and then after that we put it to the chamber. And then after the student finished collecting the data, we take out the sample, we put it into the guard box, and then we hope that okay, maybe next time we come back to measure it. So it turns out that the next day, when they take out the sample is gone. Yeah. So it is just gone. Yeah, even we put it into the guard box, it's for a day. Yeah. So it turns out that again, it's very sensitive to the moisture. So for this sample 2 and sample 3, we the students prepare the device under the guard box. Okay. Okay, so what's the mechanism of the very nice thermal signal that we observe? Is it purely driven by the phonons? And the answer is no. And the reason is because if the thermal signal that we observe is purely driven by phonons, then we will expect the thermal signal is going to increases with the magnetic field, and at zero magnetic field, the thermal signal should be zero. But in reality, again, we observe thermal signal even at zero field, right? So this again tells us that it's not purely driven by the phonon. Okay, so we can exclude such a possibility. The second possibility is that it's possible that it's mainly driven by the phonon thermal effect induced by the internal magnetic field of the magnetization, because the system is ferromagnetic, right? And we could also kind of exclude such a possibility by comparing the field dependence of the magnetization and the field dependence of thermal conductivity going to the high field. You can see that when I go to the high field, the magnetization saturates, while the thermal conductivity continues to decreases. So this immediately tells us that again the thermal signal that we saw here is not really related to the internal magnetic field of the magnetization. So instead, it's something related to the magnetic excitation. Because as I mentioned earlier, when we apply magnetic field, the magneton bands will be pushed up to the higher energy. Therefore, the thermally populated magneton particles will have less number, less population. Okay, and that's the reason that we are going to get a decrease in the thermal signal. To further understand the mechanism of the thermal signal that we observe here, so we collaborated with the theorist who did the band structure calculation as well as the thermoconductivity calculations. So the calculation was done based on the 2D Hamiltonian on the honeycomb lattice. So this is the Hamiltonian, where we consider the first 3 neighboring interactions within the plane. And then the fourth step here is the DM interaction, and this time is the anisotropic interaction and the GV interaction. So naturally, without the DM interaction, we can see that the magneton bands cross each other. But if we take into account the DM interaction, then the magneton bands will open a gap at a K point. So around this gap opening point, we see a very large Berry curvature. And such a large Berry curvature is going to give rise to large thermal conductivity. And again, as we can see from this equation here, right? And the figure on the bottom right just shows the comparison of our experimental data with the calculated results with 0.2 MeV DM interaction. And we can see that the experimental results, which are shown by these red symbols, agree very nicely with the theoretical results. So this kind of suggests that in high temperature, our thermal signal is dominated by the topological magnons, as what we hope to see. But in the meantime, we have to see that at low temperature, there's a large discrepancy between the experimental data and the calculated results. So what's the cause for such a discrepancy? So as I mentioned earlier, from the longitudinal thermoconductivity measurements, we know that the system shows a very strong magneton phonon scattering, right? So naively, this might be something related to the magneton phonon scattering. But before we address this question, here we plot the difference between the experimental results, between these experimental results and the calculated results. And we plot this difference as a function of temperature. The result is shown by this blue dot. And we can see that they got two peaks. We can just forget about the high temperature peak because this is the artificial feature. Our thermal Hall conductivity was calculated based on the mean field theory, which could not capture the fluctuation phenomena near the phase transition. Okay, so again, this is the artificial feature. Now let's just focus on the low temperature peak, the peak in low temperature. In this graph, I also plot the temperature dependence of the longitudinal thermal conductivity. And we can see that these two curves almost maximize at a similar temperature. So this tells us that in this system, the low temperature thermal Hall conductivity must be something related to the phonon. But as I mentioned earlier, it could not be purely driven by the phonons. Magnetism must be something must be involved. So how does the phonon play a role here? So as I just mentioned 1 minute ago, in this system, it shows a strong magnon phonon scattering. Therefore, our theory collaborated did some phonon calculations by considering or by taking into account the magnon phonon scattering. The top two figures shows both the phonon and magnon dispersions with and without considering the magnon phonon scattering coupling. Okay, and the blue curves are the phonon bands, the red curves are the magnon bands. So we can see that if we take into account the magnon phonon coupling, you can see that the magnon phonon bands will hybridize. For instance, if here I zoom in the low energy one, you can see that the magnon and phonon bands intercross each other in the hybridize. It's going to form a new particle, so-called magnon polymers. And along this anti-crossing point, it would have these bands would have very large value curvature. And the value curvature is so large, it's even larger than the value curvature induced by the DM interaction. And since this anti-crossing occurs at low energy, right? So of course they are going to contribute to the low temperature thermal Hall conductivity. And this is exactly what we see in the calculated results. The green curve is the calculated thermal Hall conductivity taken into account the magnon phonon scattering. And immediately we can see that at a low temperature, indeed it captured some of the thermal Hall conductivity that we observed experimentally, right, at low temperature. And the figure on the right just shows the temperature dependence of the anonymous thermal Hall conductivity, anonymous thermal Hall angle, which is defined as the ratio of thermal Hall conductivity to longitudinal thermal conductivity. And basically, we can divide this figure into two regions. For the high temperature regions, the thermal Hall signal is dominated by the topology magnons. And at low temperature, the thermal Hall signal is dominated by the magnon phonon hybridization. Okay, so here's just a brief summary on the vanadium triiodide. We observe large enormous thermal Hall effect, and it has the thermal Hall effect has a dual nature. At high temperature is dominated by topology magnons. At low temperature is dominated by the magnon phonons due to the magnon phonons coupling. So for the next few minutes, I would like to switch the gear to talk about chromium triiodide, because this is the sample that motivated our study, right? So we might wonder, so what happened to chromium triiodide? Did we try to measure the chromium triiodide? And the answer is yes. Actually, as a matter of fact, chromium triiodide was the first sample that we measured, but we did not see any signal at a higher temperature. Okay, so this really important to us a lot. So, and then after that, then we switch to chromium triiodide. But anyway, coming back to chromium triiodide. So this is the thermal Hall data that we got. It shows the field dependence of the thermal Hall signal of this compound measured at several different temperatures. And then again, from this data, we will extract the temperature dependence of the thermal Hall conductivity. Right? And here, again, related to Martin's question, here we made multiple samples. Here I just show two. You can see that the signal are the behavior of these two samples are very comparable to each other. There are two features I would like to point out. First is at low temperature. Again, the thermal Hall signal maximizes. Right? It peaks somewhere about 10 Kelvin. And for both samples, it turns out that this peak position is almost the same as the peak position that we can see from the longitudinal thermal conductivity. So again, this tells us that similar to the vanadium triiodide, for the chromium triiodide, at low temperature, the thermal Hall signal can be dominated by the magnon phonon coupling. Interestingly, or surprisingly, at high temperature,
we did not see any, or we see very small thermal Hall signal. So what's the reason for that? So if we assume that at this high temperature, the small thermal Hall signal really comes from the topological magnons, as what we found in the vanadium triiodide case, then we will expect, that the DM interaction, okay, will be much smaller than what we expected based on the universal neutron scaling data. So by comparing the experimental data with the equation, we found that the threshold value of the DM interaction, assuming that it's a dominating factor for the thermal Hall signal at high temperature, then the threshold value of the DM interaction is about 0.01 MeV. Okay. So again, what's the possible reason, potential reasons for the small thermal Hall signals that we observe in chromium triiodide? So there's a more recent in neutron scaling measurements on chromium triiodide, and all this in this paper and also in the previous PRX paper, all the measurements was done on core-aligned chromium triiodide samples. By the way, again, the samples were grown using a chemical vapor transport technique. And if you are familiar with such a technique, usually the sample that you could grow is very, very small. Therefore, you need to really core-align a huge amount of the sample for the universal neutron scattering experiments. Okay, so anyway, in this more recent universal neutron scattering experiments, they core-align the samples with a much smaller sample module, and then they found out that the magnon gap is much smaller than what they found initially in the 2018 PRS paper. And they found that, well, as a matter of fact, the sample module contribute to the magnon gap opening at a K point. So for instance, I did some simulations. The middle figure shows the linear spin wave simulation without the DM interaction, but considering the sample module, 8-degree sample module, we can see that indeed there's a magnon gap opening at a K point. This is kind of similar to the experimental data. Okay, but in this paper, they found that or declared that the system still shows, or the system still have 0.09 MeV DM interaction, which could get a benefit to the experimental results. So again, the sample module could contribute or could artificially introduce a magnon gap at a K point. And such a feature has been observed in the sister compounds. For instance, in the chromium tribromide. Again, in 2021, there was a paper published in PRB which found that they observed magnon gap at K point. And again, they found they argue that this system shows the topological magnetic stations. Like 1 year later, there was another paper by Gruber in PSI, who measured a single piece of chromium tribromide. They did not observe any magnon gap. Okay. So again, the magnon gap opening at K point would come from the sample module. And again, similar conclusion has been reached by a group in Oak Ridge National Lab done on chromium tribromide. They observed the direct magnons instead of operating magnon insulator. Okay, so again, so here's the kind of potential question is it possible that the intrinsic DM interaction in chromium triiodide is smaller than 0.09 MeV? It was initially argued based on the universal neutron scaling results. So another potential reason is that maybe it's something related to kind of combine the effect of the interlayer interaction and the further neighboring intralayer interaction. So in this theoretical paper, they found out that the thermal Hall conductivity in chromium triiodide is very sensitive to both interlayer interaction and the third neighbor intralayer interaction. So from this phase diagram, we can see that the thermal Hall conductivity will change the sign, right, from negative to the positive. Okay, and it turns out that in this interlayer calculation, we found that within some kind of phase parameters, the system could have the magnetic station of the system could undergo topological phase transition from topological magnon insulator to the wire magnons. So within such a phase parameters, the thermal Hall signal could be very small. Okay, and maybe this is something contributed to our observation of the small thermal Hall signal in chromium triiodide. Okay, since I'm running out of time, so I'm just quickly show you our recent thermal transport studies on another compounds, which is iron dichloride. So iron dichloride has a triangular lattice of magnetic iron ions. And this system orders antiferromagnetic with the near temperature about 21 Kelvin, and it has an A-type antiferromagnetic ordering with the EGSs pointing along the C direction. And apparently from the visual structure, you can see that it's one of us magnet as well, with very weak interlayer coupling. And as a result, when we apply magnetic field along the CSs, we are going to see a metal-magnetic phase transition. And interestingly, when we do the thermal transport studies, we found out that the system shows a very large magnetothermal conductivity. You can see that the interfaces of the 9 Tesla, the magnetothermal conductivity reaches almost 700%. It's very, very large. And we also did the thermal Hall transport studies. And again, we see a very nice thermal Hall signal. And below the transition temperature, we can see even the sign change of the thermal Hall signal, which corresponds to the metal-magnetic phase transition induced by the magnetic field. And again, such a thermal Hall signal could be something associated with the magnetic-phonon hybridization. And the magnetic-phonon hybridization was kind of studied about 40 years ago through the unidex neutron scattering measurements. And here's the data, neutron scattering data. Okay, so I guess I'm running out of time. So here's the kind of acknowledgement. I would like to thank my students at Michigan State University for these studies. And of course, I would like to thank our theory collaborators for this research group in the University of Michigan who provided our theoretical support. Thank you very much.
Questions, please. So the first part of your talk,
Yes.
you showed kappa XX. It
Uh-huh.
looked like it was linear in temperature at low temperature.
Kappa XX is
Kappa XX.
Yeah, is linear a low temperature. Okay, so I don't think it's perfectly linear. Unfortunately, we did not really take a close look.
But it's, I mean,
We might be able to fit it with the TQ.
I mean, Q is what you would expect.
Yeah.
It looks much weaker than that. Okay.
Okay, that good point. Yeah, let me go back to take a close look at the data later on. Yeah.
Ask a related question, at high temperatures, kappa is also still rising. I mean,
A high temperature?
yeah, what happens? I mean, it does eventually. start to go.
Yeah, and so unfortunately here we use the sound sensor, so we did not go above 100 Kelvin. And for this particular data, we want to put in maybe 80 or 90 Kelvin. So, but I would again, I would expect that it should go down when it goes to higher temperature.
Yeah, I have a question. So, kind of big question. So first, can those materials be encapsulated? And second, can those materials be studied with electrical transport?
So again, this material, for the second question, this material are insulating compounds, therefore we cannot really do electric transport. So we try to use the ohmmeter to measure the resistance at room temperature. We could not measure it using the ohmmeter. Related to the first question, no, we did not calculate this system. And again, this system is very area sensitive. So as I mentioned, at the end, what we did is we make the device inside the car box, and then after we finish fabricating the device, immediately we put it into the PPMS chamber within maybe 1 minute. And hopefully by doing that, we could avoid exposing the sample in there for the moment. So and degrading the sample. Yeah.
I have two questions. The first one, the basic question. So you mentioned it's anomalous thermal Hall effects. I'm wondering how does the non-anomalous Hall curve look like? And the second question is, you mentioned the mosaic in chromium iodide could introduce those magnetic gaps. I assume the mosaic is basically in plane. So you should see the magnetic dispersion smearing along the transverse direction. So I'm not understanding why this can introduce a gap.
Okay, so first of all, what's the question? If it's not anomalous, then we will expect to see zero thermal Hall connectivity in zero magnetic field. But here we see a very nice thermal Hall signal in zero magnetic field. Sorry, what's your second question?
So I'm not understanding how the mosaic can introduce a gap because I assume it's just smearing the magnetic dispersion along the transverse directions.
Mosaic, okay, so okay, so the thermal mosaic, the question is that where, for example, let's say that here, okay, you just look at this data, right? You can this is the experimental data, and you can see that they integrate error in order to see the intensity. Right? They integrate a large error range in a momentum space, and this actually corresponding to our Christians maybe know much better than me. In this case, I think this means that somehow you include or equivalent to the case that you include a large mosaic of your sample. Okay, but just look at the middle graph, right? You can see that in this calculation it included the sample mosaic. Let's see. Yeah. So because again, if your sample is the sample mosaic, imagine that initially you will say, well, okay, I'm measuring along K point, but in reality, you are not really measuring a K. You are not really measuring a K point. You are measuring a momentum point slightly away from the K point, and as a result, the intensity could be different. Yeah.
Yeah, I had also a comment that, especially for layered materials, changing the geometry, so you measure a thermal current in the C direction is a very good way of deconvolving the phonon contribution from others, because basically only the phonons propagate in that direction.
Yeah, this is a very good point, but unfortunately, in reality, it's extremely challenging to measure to apply the thermal gradient on the C direction. The thickness of the sample that we measure or that we grow is somewhere in the order of several tens micrometer thick. So yeah, so it's also almost mission impossible for such a measurement.
Yeah, so you measure, you show this explanation where you have the phonons crossing the nylon bands and the hybridization and the redistribution of Perry curvature. But I mean, do you have inelastic neutron scattering showing all that? Or?
Yeah, so again, very good question. So in the last last year we tried to colonize 1,000 pieces of vanadium triiodide inside the garbage. My students spent 3 weeks, 4 weeks, something like that. We spent 4 days trying to do the experiments on high spectrum. Didn't see anything. Yeah, important. We did not see anything, but it's just because the sample mosaic is too big, way too large. Because again, the student need to colonize the samples inside the glove box under the microscope. It turns out that the quality of the colonized sample was just too bad. Yeah, so we did not see anything.
Maybe I can ask one final question. So this hysteresis loop of low temperatures, it was the same for the Comin system you showed. They look shifted along the field axis, and they also look like they have asymmetric.
This one?
No, but very low temperatures.
I don't think it's appeared along the axis.
Really? 13.5 Kelvin, that loop looks the same on the right as the left.
Fine. Okay. Okay. Yeah. Maybe I should take a closer look.
Yeah, and it didn't in the Comin metal either. I was just wondering.
So for the Comin metal, oh, you are talking about for the Comin metal. Yeah, for the Comin metal, again, we are thinking that there's some kind of exchange bias going on in the system. Exchange bias.
Yeah, but for
okay. From what we are thinking that maybe there's some kind of coupling between in the Comin systems. We are thinking that there's some kind of persistence of ferromagnetic phase and the spin gas phase in the system, which lead to the exchange bias. But in this system, I need to take a close look at the data, but I don't think it's very
all right. Well, thank you very much again.
We'll meet again at 1:20, and it's a little under an hour and a half.
Can we leave our stuff here?
Better take with us. Maybe the